PreCalc. Here we are with our introduction to limits. This is the calc part of PreCalc, so buckle up and enjoy. The notion of a limit is a fundamental concept of calculus. We will learn how to evaluate limits and how they are used in the two basic problems of calculus, the tangent line problem and the area problem. You are given 24 inches of wire and are asked to form a rectangle whose area is as large as possible. Determine the dimensions of the rectangle that will allow you to produce the maximum area. Okay? It appears that the maximum area occurs when W is 6, as shown in the table. So if you have 24, whatever this is, you're going to double it, and then you would have 12 minus W for your length. Because you'd have 2L, well, let's show you here. P equals 24. 2L plus 2W equals 24. So if we divide everything by 2, L plus W equals 12. So then L would equal 12 minus W. Alright, so that's how they're getting that. So as your W, let's say you start at like 2, 3, 4, 5, your area would be 35, could be 5 times 7. 5.5 times 6.5, you'd have 35.75. As you keep building up, you're going to get up to 35.999, 36, and then we're going to cross back over to 35.9999. Because now that our width is 6.1, that's going to leave our length to be 5.9. And when our width is 6.5, now our length is 5.5. So we're going to be getting those same answers. So you can see, as you come in from both sides, we're kind of squeezing in and middling on a square. Length of 6, width of 6. And the area is 36. In limit terminology, you can say the limit of A as W approaches 6 is 36. If f of x becomes arbitrarily close to a unique number L as x approaches a constant number C from either side, left side or right side, the limit of f of x as x approaches C is that L. This is written as the limit as x approaches C, that's going to be a constant number like 3, 4, 5, of f of x equals the limit L. Okay, I'm going to walk through one with you, and then you're going to do one on your own. Okay? Of course, I'm going to do the easy one with you. It's a line. It's a line. Okay, 3x minus 2. So if I plug in 1.9, see if I can get the calculator to show up. I don't have my good one with the glow screen. Alright, so we're doing 3 times 1.9 minus 2. I got 3.7. 3 times 1.99 minus 2. 3 times 1.999 minus 2. And even though we can actually do 2 with this one, we're going to skip it. So we have 3.7, 3.97, 3.997. We're going to skip 2 because that's where this limit process comes in handy, is when we actually cannot do that value. Okay, and let's go down the other side. 3 times 2.001 minus 2. 3 times 2.01 minus 2, and 3 times 2.1 minus 2. We got 4.003, 4.03, and 4.3. 4.003, 4.03, 4.3. And you can see as we come from one side and the other side, we're squeezing in from both sides. We're coming in at, we're approaching 4. We're approaching 4 from both sides. So the limit as x approaches 2 of 3x minus 2 equals 4, which we could have done on the graph, right? Because that one, there's no problem with that. Okay. What if you had the next one? You could probably do the next 2 on your own. Well, we'll start with this one. Okay, limit as x goes to 0 of x over square root of x plus 9 minus 3. Note that the x plus 9 is inside the square root and the minus 3 is not. So you have to be careful typing that in. And you can't just type in 0 this time, because 0 plus 9 would be 9, and the square root of 9 would be 3, and 3 minus 3 would be 0 on the bottom. Okay? So this is where this comes in handy. Let's have you push pause and fill in that table. All right, welcome back. Okay, let's practice typing that in if you didn't have success typing that in. If I start with negative 0.1, I'm going to go alpha y equals for my fraction bar. And I'm going to have negative 0.1 on the top, square root, negative 0.1 plus 9, get out of the square root, minus 3, and now get out of the fraction. Okay, I got 5.98, blah, blah, blah. Okay, now to change it, I might do second enter. Let's see if it's going to let me second insert a 0 there. Perfect. We can just keep going down. How did I get it? 59. Interesting. Let's try that again. 59. Let's go negative point. It should have been the same thing, just change the decimals a little bit. Negative 0.1 divided by, parentheses, square root, negative 0.01 plus 9, outside of the square root, minus 3, close it. Well, you got us stumped here. It should be, maybe you were getting the same thing, maybe mine's malfunctioning just today for whatever reason. We should be getting 5.98, 5.99, 5.999, and then on the other side you would have 6.000, 6.001, 6.017. Okay, and as those squeeze down, we should be getting closer to 6. I don't know why mine's jumping to 59. 5.9. One more time. This is frustrating. All right, fraction bar. Boom. We got, let's even do this, parentheses negative 0.01. Divided by square root, parentheses negative 0.01 plus 9 outside of the parentheses minus 3. There we go. Must have been something with the negatives that it didn't like. 5.998. Okay? And it's going to keep squeezing in closer to 6. All right? We got another one. Another limit. Another limit. We're plugging in 2 this time. We're plugging in 2. We're trying to find the limit as x goes to 2. And again, we can't plug in 2 because 2 minus 2 would be 0 on the bottom. We can't have that. Okay, so push pause and give it a go. Let's see what we got. All right, this time we should be getting 5.61, 5.96, 5.996. On the other side, we have 6.004, 6.04, and 6.41. And again, we're squeezing into 6. And we're squeezing into 6. So we could say the limit as x goes to 2 of x to the third minus 2x squared plus 2x minus 4 all over x minus 2. That limit equals 6. We're learning. So far it's kind of common sense that if it's kind of squeezing together, then that's what it is. This one we could actually do, right? We could have tossed 2 in there and it would have worked. Okay, these are where it starts to get interesting because I couldn't plug those values in. I couldn't plug those values in, so that's where the limit starts to become useful and helpful. Turn the page. Graphically, let's think about it graphically. Find the limit of f of x as x approaches 5, where f is defined as 1 everywhere that isn't 5, and at 5 it's negative 2. So at 5 it's negative 2, but everywhere else it's 1. So open dot there. Okay, so everywhere else it's 1, except exactly at 5, then it's negative 2. So it's 1, 1, 1, 1, 1, 1, 1, 1, 1, boop, negative 2, boop, 1, 1, 1, 1, 1, 1, 1. So as we approach from the left, and as we approach from the right, it's solid 1s. So even though the actual answer of the function is negative 2, our limit is going to be 1. Because as we get infinitely close, it's still 1. You could have 4.999999999. It's still 1. At 5, it jumps to negative 2. And at 5.00000000001, it's back to 1. So it's 1 everywhere. So the limit is 1. That's a tough concept to kind of grasp. That even though it it equals something else, the limit is 1 because that's what it's approaching from both sides. Okay, example 6, they give you the graph. And this is where we talk about, the book didn't really talk about left and right side until like right now. We're kind of talking about it in this problem, but it didn't talk about it leading up to it. So as I'm coming in from the left, my limit is -1. And as I'm coming in from the right, it's +1. And so far, everything we've done has been the same as I came in from the left and the right. Well, this time it's not. This time they disagree. And when they disagree, then it said the limit does not exist. So the limit, as x approaches 0, and then we're going to do a negative sign because I'm coming in from the negative side, or the left, that is -1. And the limit as x approaches 0 plus from the positive side, or the right, equals +1. They don't match. Okay, they don't match. Not the same. So, the limit as x approaches 0 of the absolute value of x over x does not exist. Does not exist. Or DNE. All right. Discuss the existence of the limit as x approaches 0 of 1 over x to the 4th. So we're going to type it in, and we're going to look at it. Y equals 1 divided by x to the 4th. Not 1 over x, parentheses to the 4th. 1 over x to the 4th. Okay, so as I'm coming in from the left, it goes up to infinity. And as I come in from the right, it goes up to infinity. Okay, so you might say, oh, they both go into infinity, so the limit is infinity. But let's rewind. Let's rewind. If it becomes close to a unique number, L, okay, infinity is kind of an idea or a concept. It's not a number. It's not a number. It's not like 1, 2, 3, 4, 5, okay? You can keep counting forever, but the idea of forever is infinity. So it's not a unique number, okay? So as x approaches 0 from both sides, one over x to the 4th increases without bound, never approaches unique number, therefore limit does not exist. Limit as x approaches 0, DNE does not exist. All right, so we had limits that don't match, does not exist. It looked like it matched, but it does not approach a unique number, so it does not exist. And let's see what our crazy one here is. The limit as x approaches 0 of cosine of 1 over x. Cosine of 1 divided by x. Flat lines and then dips down and comes back. We're going to zoom in, maybe do a zoom box. You get to use your little cursor and draw a box. Top left corner. You can just zoom in repeatedly. Let's see what we got. Boom. Okay, so what looked like it was just a little dip, but it actually comes down and goes crazy in there, and then it resumes normal. And if you actually zoom in even some more, if I just did zoom in, I didn't do zoom box, I just did zoom in, you get closer, you can see it just goes really crazy. It's going really crazy in there. Okay? So it's oscillating, it's bouncing back and forth really fast, so it's never approaching a unique number. So again, the limit does not exist. Another reason where the limit would not exist. As x approaches 0 from both sides, fancy word, cosine of 1 over x oscillates, bounces back and forth rapidly between -1 and 1, so never approaches a unique number. Limit D-N-E does not exist. So it's kind of an exploratory problems there. Some exploratory problems. And now they're going to tell us the rules. Conditions under which the limit would not exist. The limit of f of x as x approaches c does not exist if any of these conditions are true. If f of x approaches a different number from the left side and the right side of c. If f of x increases or decreases without bound, goes to positive or negative infinity, not approaching a unique number. Or if it oscillates between two values, then it would not approach a unique number. And that would be another does not exist. Okay? You have seen that sometimes the limit of f of x as x approaches c is simply f of c. Like the first example, we could have just plugged it in. It is said that the limit can be evaluated by direct substitution. A lot of the times you can just plug it in, direct substitution. There are many well-behaved functions, just like there are many well-behaved students, such as the polynomial functions and rational functions with non-zero denominators have this property. You can just plug them in. Okay, there's a list of things that you can probably just plug them into. Properties of limits. If the limit is x approaches c of f of x equals L, and the limit is x approaches c of g of x equals k, what can we do? You can do a scalar multiplier. If you have a times b, 3 times f of x, it's going to be 3 times the limit. You can add or subtract those two together. If I add those two functions together, I'm adding those two limits together. If I multiply those two functions together, the limits would be the product as well. And you can divide it so long as k doesn't equal 0. You can do a power. The limit as x approaches c of f of x to a power is the same as the original one, the original limit value to that same power. Okay, a lot of these are going to be direct substitution or using those properties. Let's have you think about those and give those a shot now. All right, let's see what we got. A lot of these we can just plug them in. So 4 squared, no sweat, that's 16. 5 times 4 is going to be 20, no big deal. Tangent of pi over pi. Tangent of pi over pi. Tangent of pi, that's sine over cosine. Sine of pi is 0, cosine of pi is 1, 0 divided by, or negative 1. 0 divided by negative 1 would be 0, and 0 over pi would be 0. Square root of 9, we're going to call it 3. If you wrote plus or minus 3, that's fine. Pi times cosine of x. Pi times cosine pi. Cosine of pi is negative 1. And our answer there is going to be negative pi. And here we'll have 3 plus 4 for 7 squared, 49. So a lot of them are nice ones that you can just plug them in. Okay, and that's not, the limit part isn't really needed there because we can just plug those in. The limit is really useful for things that we can't plug in. When evaluating limits, remember there are several ways to solve most problems. Often a problem can be solved numerically, graphically, or algebraically. The limits in example 9 that we just did are found algebraically. You can verify the solutions numerically and or graphically. To verify the limit in example 9a numerically, you could create a table to show that they are getting closer to 4 from left and to right. If p is a polynomial function and c is a real number, then the limit as x approaches c of p to the of p of x equals p of c. Polynomial functions, you can just plug it in. If r is a rational function, then we can plug it in so long as q of c, the bottom, does not equal 0. Okay, more fun. All right, we're doing limits, which is a big idea, but we're also doing it in a very lower level way right now because it's just the intro. Okay, so again, does it make it equal 0? Does it make the denominator equal 0? If not, then I can probably just direct substitute. So we're going to plug 2 in. We'll have 2 squared plus 5 times 2 plus 4. 18. Okay? Does 2 make the bottom equal 0? No. So let's have you kind of mentally think about that one. Maybe do the top mentally, do the bottom mentally, and then divide. All right, if we're plugging 2 in, we just did the top there. 18 across the top, and 2 plus 4 is 6 on the bottom, so our limit would be 3. Okay, introduction there to limits. Not everything's going to be super easy where we can just direct substitute, but that's how a lot of well-behaved functions work. We will be using this kind of stuff more and more, looking for how things approach from both sides, making sure it matches up the same way we did over here. Making sure things match up. All right, hopefully you survived day 1 of limits. We'll be moving on to more complicated pieces of that in upcoming lessons, but thanks for following along, and you should have a worksheet to do now. Good luck.